Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asgar, and we were talking about the synthesis and design of inorganic materials under the subject of advanced inorganic material chemistry. Dear student, we have discussed in previous lectures that about the solid state reaction and shake or bake method, and we have studied some of the important aspects of solid state reactions, which also include the nucleation and growth, epitaxy and topotaxy. Moreover, we have discussed the some of the reactions for the synthesis of interfaces magnesium oxide, aluminum oxide, and more importantly, the practical considerations of solid state reactions. In the practical considerations of solid state reactions, we have discussed about the four major important points that we need to observe or we need to obey before performing the solid state reactions in shake and bake method. The first one was the starting materials, and the second one was the mixing of reactants, while the third one was the container. We should have to choose the container in a proper way, because sometimes some containers may not be suitable for all kind of reaction mixtures. And the last one was the firing schedule. Now, after discussing these factors and the conditions for the solid state reactions, now we are able to discuss some of the important examples about solid state synthesis and the reactions. And we should uh, also we are now able to discuss some of the problems related to the synthesis of inorganic compounds, and we will provide the possible solutions. For example, in case of lithium sulfate Li4SiO4, lithium sulfate is actually is a parent phase for a family of lithium ion Li positive ion. It is actually a parent phase for a family of lithium ion conductors, and that can be prepared by using this kind of reaction in which lithium carbonate and silicon dioxide reacted together at about 800 degrees Celsius for one day, and it will yield the Li4SiO4, and the carbon dioxide gas evolved as a byproduct. So the problem is actually the lithium carbonate usually melts and decomposes readily above 720 degrees Celsius. It is reactive towards most container materials, even including platinum and silica glass. So, what would be the solution for the Li4 lithium carbonate Li2CO3? Actually, we should the solution is actually we should have to use the gold containers, carrying out decomposition and pre-reaction of lithium carbonate at 625 degrees Celsius for few hours before final firing at about 900 degrees Celsius overnight. So instead of using silica glass container or platinum container, we better to use gold container, which is more unreactive towards lithium carbonate. Moreover, the pre-reaction of lithium carbonate should be done below 720 degrees Celsius, because this is actually the readily decomposed temperatures. So the optimum temperature for this is about 650 degrees Celsius, and we should have make a pre-reaction at this temperature before the final firing, which is 800 to 900 degrees Celsius. The second example is YbA2 to infinity. This is actually the classic 900 Kelvin superconductor, and it can be prepared by using the following reaction, in which Y2O3 will be reacted with barium carbonate BaCO3 and copper oxide CuO with the limited supply of oxygen, or half mole of oxygen, at about sometime 950 degrees Celsius. The problem is barium carbonate is particularly stable on heating, and it can be difficult to remove the last traces of carbon dioxide during reaction. There is also many materials such as YbCO which may react slowly with atmospheric carbon dioxide, causing a partial reversal of the reaction used in the synthesis. And the second problem would be the CuO is reactive to most of the container materials at elevated temperatures. The third one is actually the oxygen content. 7 to infinity of the YbCO product is variable and must be controlled to optimize Curie temperature. So solution for these problem is actually the first one is actually the react of the react in a carbon dioxide free atmosphere with barium nitrate as a source of barium oxide. So we can use better barium nitrate, as actually we need a source of barium oxide, so we better to avoid the carbon barium carbonate, because it is somehow is reactive with the carbon dioxide. Moreover, make pellets of reaction mixture and react these on a bed of pre-prepared YbCO. After reaction at 950 degrees Celsius, carrying out a final heating at 350 degrees Celsius to allow oxygen uptake to occur and achieve the desired stoichiometry. So this is all about this one. The next example is sodium beta beta alumina. So this is actually the classic sodium ion conducting solid electrolyte. In reality, there are two sodium aluminate phases whose formula are written ideally as Na aluminium 11O17, it would be the beta form, and Na aluminium 5O8 is beta double dash. Although both phases form solid solutions with the variable sodium aluminum ratios, and they can be prepared as follow, in which sodium carbonate is reacted with aluminium oxide in the temperature range of 1500 degrees Celsius, and they will form the sodium beta beta double dash aluminas. So there will be a variable content of sodium in this compound. The problem is sodium oxide Na2O is volatile at required reaction temperatures. Lower temperatures cannot be used because of the inertness and unreactivity of alumina oxide. Now let us talk about the solution of the problem, which is actually the carry out pre-reaction at 700 to 800 degrees Celsius and expel carbon dioxide gas. fabricate green pellets or tubes of the partially reacted mixture and cover the pellets or tubes with pre-reacted beta double dash alumina and fire at 1400 to 1500 degrees Celsius. This buffering prevents significant loss of sodium oxide from the samples at high temperatures. Number two is use high surface area reactive alumina react starting materials such as bohemite. These have a defect spinal structure which is quite similar to the beta double dash alumina product, and the first stage of reaction involves an intercalation of sodium ion into the particles of alumina. This greatly assists the nucleation and growth of the product since the reaction is partially topochemical. So that would be the best solution for the said problem. The above examples are all oxides. For the synthesis of non-oxide by solid state reactions, similar criteria apply, but methodologies are often completely different. As we discussed for the synthesis of oxides, the for the synthesis of non-oxide by solid state reaction, we can devise the similar criteria, but methodologies may be different. For example, a versatile method for the synthesis of carbides, borides, and nitrides in carbothermal reduction, which was developed by the Hutchison process to fabricate the silicon carbide SiC, which is an important ceramic used as an abrasive and carbobundum and in furnace heating as a furnace heating elements. This is actually to this process Hutchison process is actually to fabricate silicon carbide from the mixture of silicon dioxide SiO2 and carbon using the following overall reactions, which is SiO2 and the carbon. They are reacted together and form silicon carbide and carbon monoxide gas. This is high temperature reaction in which both carbon is actually a both reagent and reducing agent for silicon dioxide. The reaction mechanism is complex and involves silicon monoxide SiO as a gaseous intermediate, which is very effective in bringing the silicon and carbon reactants into the contact. Various other carbides can be made by carbothermal reduction, including Al4C3, B4C, TiC, WC, and MO2C. These are the different carbides that would be synthesized by using carbothermal reduction method. Borides can be prepared by a similar process, but the boron reagent is B2O3, which needs to be reduced to the elemental boron. Carbon is therefore added to the reaction mixture to achieve the reduction of both B2O3 and the metal oxide. although it should not feature in the boride product. Examples of borides synthesized in this way include the aluminum boride Al-B12, Vb, Vb2, and Tib2. Nitrides can also be prepared such as Bn boron nitride, aluminum nitride, silicon nitride Si3N4, and titanium nitride TiN can be prepared similarly using a reagent as a reagent the metal oxide, nitrogen gas, and carbon. And this was all about beta and beta double dash alumina. Now let's talk about the combustion synthesis. In complete contrast to solid state reactions that often require heating for several days at elevated temperatures to complete a synthesis process. So we need a controlled explosions in reactions which is known as combustion synthesis or self-propagating high temperature synthesis SHS, and a solid state metathesis SSM, solid state metathesis, which can give us the reaction products in minutes or even seconds. So the combustion synthesis process is supposed to be the quite reactive and quite speedy in nature, and it will provide the sometimes the products even in seconds. And in SHS method, which is actually the high temperature synthesis, we can say self propagating high temperature synthesis. It is actually pioneered by Russian scientists. Starting materials are chosen that react together exothermically. Consequently, once a reaction is initiated, enough heat is generated for high temperatures to be attained and complete reaction occurs rapidly. The starting materials may be classified as either fuels or sometimes oxidants. An example of an SHS reaction, which is actually the self propagating high temperature synthesis, is the thermite process for the extraction of iron. Here we can see that in thermite reaction the iron oxide Fe2O3 reacted with aluminium, and it will yield the iron and aluminium oxide. In this reaction, in which the fuel aluminium and the oxidant Fe2O3 combine to generate temperatures of 3000 degrees Celsius for a brief period of during reaction, for a brief period during reaction. So it is kind of this is actually the self propagating high temperature synthesis, which is shortly known as SHS technique, and it is actually the thermite process for the extraction of iron, in which the fuel aluminium and the oxidant Fe2O3 are actually combined to generate temperatures of 3000 degrees Celsius for a brief period during the particular reaction. In other combustion synthesis, the fuels and oxidant are additional reagents that are consumed in the reaction and do not features in the final product. The typical fuels are hydrazine, glycine, and urea, Common oxidants are nitrates of the one of the reacting species. Many complex oxides can be prepared by combustion synthesis. Mixture of metal nitrates and urea in stoichiometric amounts to maximize release of energy are heated in a vitreous silica crucible to 600 degrees Celsius, at which the temperature self-ignition occurs to give the spinel product in a very short time. The resulting material is actually a fine powder, since gas evolution during reaction prevents agglomeration. Agglomeration was actually the process in which some of the particles may combine together and form the a big chunks. So it will reduce the agglomeration process. The powder may be then to be pressed into pellets and heated at high temperatures to give dense ceramics. Temperature control is quite an important, since heating below 1100 degrees Celsius may lead to the incomplete densification, whereas above 1300 degrees Celsius exaggerated grain growth (EGG) occurs to give a ceramic with an inhomogeneous texture. In a closed in a closely related SSM reactions, the reactants are choose that such that one of the products has a high has a very high lattice energy, and its formation provides during the driving force for the reaction. An example is this one is actually lithium Li3N and TaCl5, which produce TaN and lithium chloride and nitrogen gas, in which covalent TaCl5 and highly reactive Li3N form the desired product, which is TaN, together with the lithium chloride, and lithium chloride may be dissolved readily to leave pure TaN. And SSM methods are usually better controlled than SHS method, since the boiling or the volatilization of the side products reduces the driving force for the reaction, uh, and therefore limits the temperature attained during the synthesis to that boiling point of the side product. A wide range of material may be prepared by SHS and SSM methods, and various carbon related materials including carbon nanotubes can be prepared by SSM of lithium acetylide. And we can see that many carbides, silicates, nitrides, phosphides, sulfides, and also many oxides can be prepared by SSM method, such as ZrCl4 and reacted with Al4C3 and produce zirconium carbide. And this is actually the silver sulfide and hafnium oxide. In each case, it is necessary to carry out primarily test in order to optimize the conditions so as to obtain the phase pure products. Now let's talk about the mechanosynthesis. Solid state reactions are generally high temperature methods, and but in favorable cases reactions can be carried out simply by grinding together the reagents. High energy milling is necessary, often for the period of several hours, and therefore can be dangerous for the contamination from the milling media. The product of mechanosynthesis may be different from those of same material prepared by solid state reactions. They may be in a metastable state with compositional inhomogeneity, structural disorder, and high vacancy concentration. In a recent examples of zinc as Zn2SnO4 nanoside grains synthesized by mechanochemistry and characterized by a wide range of diffraction, microscopic, and spectroscopic techniques. Grain cores were found to have inverse and spinal structures as expected. However, grain outer shell regions and surfaces shows that zinc and SN disorder and deformed polyhedra, indicating a highly non-equilibrium state. Given the structural differences between the materials made by mechanosynthesis and conventional reactions, it is highly likely that properties may also be differ. Mechanosynthesis may become an important method for the synthesis of new nanomaterials and nanocomposites materials, which are relatively cheap and energy efficient to make, as well as for the synthesis of stable bulk materials that would otherwise require high temperature for long time periods. This was all about the shake and bake methods, and we will discuss the other methods in next lecture. Thank you very much.